In this video, we're going to look at how we can transform these basic trigonometric functions like this one here and this one here, the sine and the cosine, with expressions like this where we're adding one on, or we're doing something to the original function and what happens to the graph when we do that. So you can use either your graphing calculator. You have to change your window so that the window goes, for example, from 0 across to 2 pi and from -3 up to 3, or you could, that is if you're working in radians, or you could use GeoGebra, which is how these graphs here have been done. And just you're going to do a little sketch and put them in the little spaces here, and then you're going to try and figure out what the period and the amplitude is. So this first example, this one down here, if you graph y equals sine of x plus 1, just like that, right, with no brackets or anything, so that the 1 plus 1 is not inside any brackets, then what you should end up with is a graph that looks like this. And you'll notice that all that's happened, only difference between this graph and this graph is that here everything's been moved up by 1 unit. Right? Every point here has been shifted up by 1 unit to make this graph here. And so when we're describing that transformation, we've got to say, okay, translate y equals sine of x 1 unit up. And you'll notice that the period, again in this graph, if you go from here across to here, right, so this could be the starting point to this starting point, that's again 2 pi. You can zoom in on that to see if you're not sure. You can see that that's 2 pi from here across to here. Or if you wanted, you could go think about what's the distance between here and where we're going to be up here. Again, that's going to be 2 pi if you try that. Okay, so you should try to graph each of these and then try to describe the geometric transformation that takes place. So if you try as many of these as you can just now, and then come back to the video, I'll explain what's happening in each case. In this second example, cosine of x plus 2, what we're expecting to do here, or expected to happen, is that the cosine graph is going to be shifted up by 2 units. And in fact, you can see, if you compare this graph with this graph, that this graph is indeed the same as this graph, but just shifted up by 2 units. Okay, so you would just describe that like this. Again, the period and the amplitude are exactly the same as they were to start off with. Right? So the period is still 2 pi. The amplitude, again, half of the difference between the top and the bottom. Right? The top is up at 3, the bottom is at 1. The difference between them is 2, so half of that is going to be equal to 1. In this one here, y equals -1 plus sine of x, that's the same as sine of x minus 1. So it should be just this graph shifted down by 1. And you can see here that that is actually the case. Again, the period and the amplitude stay the same. In the next one, y equals 2 times sine of x, that should have the effect of stretching the graph. Stretching the graph vertically by a factor of 2. You can see here that instead of just going up to 1 and down to -1, that the highest point is up at 2 and the lowest point is down at -2. So the amplitude here, the distance from the middle up to the top, is going to be not just 1 this time, but 2. Okay, so here you can describe that as an expansion, a vertical stretch of factor 2. Here the period stays the same, it's still 2 pi, but the amplitude this time is 2, it's because it's been stretched vertically by 2. In a similar way, if we look at 3 times cosine of x. 3 times cosine of x should look like this, going all the way up to 3 in this case here, and all the way down to -3. And we can say that that's an expansion or a vertical stretch of factor 3. So this time the period is going to be not just 1, not just 2. Sorry, the period is going to stay the same. The period is the horizontal distance between one maximum and the next. It's still going to be 2 pi. But this time the amplitude is going to be 3 instead of just 1 or 2. In the next one, this one here, the sine of x minus 1, if you replace ever x with x minus 1, it should have the effect of shifting a graph 1 unit to the right. So if you think about what sine of x looked like, sine of x started at 0, started to go up at 0. And this one, if we zoom in on this, you can see that instead of starting at 0, right here and then going up from there, it's starting here, which is actually just 1 unit along, right? So from here to here is actually 1 radian. Pi over 2, incidentally, is roughly 1.5, 1.57. So this distance from here to here is actually just 1. So we can describe that as a horizontal translation of 1 unit to the right. Same period again, right? It's going to be the same period of 2 pi, same amplitude, 1. And it's a very similar thing for the next one. This time it's just the cosine moved 1 unit to the right. Same period, same amplitude. On the second page, or in the last page I should say, we've got sine of x plus 2. Now if you replace x with x plus 2, that should have the effect of moving things 2 units to the left. And in fact, that is what's happened here. Again, we can zoom in on this a little bit. It's actually quite hard to see what's going on here because this graph would actually continue on down here. So there'll be a starting point actually way down here, which would be at -2. So this point, the point that's usually here, that goes up like this when we have sine of x, has actually been shifted 2 to the left, so it starts actually way over here and goes up. So we can describe that as a translation 2 units to the left. The period stays the same and the amplitude also stays the same at 1. Similar kind of thing for cosine of x minus 2, except this time if you replace x with x minus 2, it shifts it 2 to the right. Same period, same amplitude. If you have y equals sine of a half x, replacing x with a half x should have the effect of expanding things horizontally, so stretching it horizontally by a factor of 2. So if you see what that looks like, it looks like this. This time, instead of us going up and down and up by the time we get to 2 pi, all that's happened is that we've gone up and down, and then by the time to get back to the starting point, we'd have to go to 4 pi this time. Right, so we'd have to go up, down, and back up again to 4 pi. And that 4 pi is, in fact, the period of this function. Right, so 4 pi is going to be the period of this one. The amplitude stays the same. So all that's changed is that instead of the period being 2 pi, it's been stretched horizontally, so now it's 4 pi. In this example, the 2 should affect the amplitude. It should expand it vertically by a factor of 2, and the 1/3 that we have here should expand things horizontally by a factor of 3. So what we'll get if we just have a part of the view of that is this graph, starting up at the top as usual, but it's going to take a long time for that to get back to the starting point. It's going to take not just, usually when we draw the cosine, we start here, we go down, and then we come back up to the starting point by the time we get to 2 pi. In this case, we'd have to keep on going until we got to 6 pi, 3 times the distance, 3 times 2 pi. Okay, so in this case here, the period is 6 pi, and the amplitude is 2. In the next one, 3 sine of 2x, the 3 again affects the amplitude. So the amplitude now, you can now see, is going to be equal to 3. Right? The distance from the center up to the top is going to be 3. You can see here, because we've replaced x with 2x, it's had the effect of compressing things horizontally. So instead of us going up and down and back by the time we get to 2 pi, up and down and back to the but for 2 pi, we're actually doing that twice. So a period is just from here across to here. The period is just going to be pi in this case. Okay, so in this case here, the period is just pi and the amplitude is 3. We can describe that by saying it's a vertical stretch of factor 3 and a horizontal contraction by factor of 2. In these last few examples, I'll just allow you to have a look at how they work for yourselves. The first one is vertical stretch of factor 3, horizontal contraction of horizontal stretch of factor 2, and then it's all shifted down by 1 unit. So we get something like this. In the next one, it should look like this. And the last one, it's a horizontal compression of factor 3, vertical stretch of factor 3, and shifted down by 3. So we end up with something that looks like this. In a case like that, the period is 2 pi over 3. Notice that's 2 pi divided by the number before the x. And that actually works for each of these, right? The period is always equal to 2 pi divided by whatever this number here is. And so the amplitude in this case here is just 3. Actually, while I'm saying that, I notice that there's an error in here. This period here should be equal to 4 pi here, not just pi. But if you see this graph here, a period there would take 4 pi. So you could change that thing here to 4 pi. Now, as a summary, if you have an expression that looks like this here, right? So you've got an a before the sign, you've got a b before either x or x plus c, and then you've got d. what's happening is that the D affects the vertical translation, the B dictates what the period is going to be, the C affects the horizontal shift, and the A is the amplitude. Okay, so if you fill in the gaps there, the first one is to say that the graphs of y equals sine of x and y equals cosine of x are translated by C units to the left, that is if C is positive. And then it's contracted by a factor of B horizontally, and then stretched vertically by a factor A, and finally translated by B units, or I should say D units up. Now, since the period of sine of x and cosine of x is 2 pi, if you contract things by horizontally by a factor of b, the period of those functions is going to be 2 pi divided by b. So if your number b, the b that's in here or in here, is, for example, 5, then the period would be 2 pi divided by 5.